guys, welcome back. It's Adam the Science Tutor here, and today we're going to be talking about enzyme kinetics. Enzyme kinetics is the speed at which enzymes help reactions catalyze and help substrates bind to different areas of a molecule. So here are our definitions for today. It's Km, and these are very important. You need to know these for biochemistry and sometimes organic chemistry as well. So Km, it equals the substrate affinity. I'm going to explain that right now. And substrate affinity is the ability for a substrate to be not just wanted, but to be attached and to be held onto. So we're going to get held onto more tight. Okay, so substrate affinity is the ability for one molecule to get a substrate and hold onto it tight and not want to let it go. That's what substrate affinity is. You'll see that with hemoglobin. That's a very popular conversation or topic point with substrate affinity. I'm going to be posting a video on hemoglobin very soon as well. Another vocabulary word is the Vmax that you need to know, and that's how quickly or how quick substrate turn to product. So that's the catalyzing, like the speed at which the catalyzation happens. And so you can see it in two different kinds of tables or plots. This is a normal plot that you'll see, and what you'll see is this is the, and this is so in here we'll see that at the top of this, at the top of this line here, you'll see this is the max. So it cannot go above a certain point. At a certain point it'll plateau and not be able to go anymore further. That is the Vmax. That is the max speed. So that is the max speed that substrate can turn into products. So it cannot go any quicker than that. The half Vmax will be half of that on the plot. So let's say this is 1 and this is 0.5. And if you get on the x-intercept or the x below the half Vmax, if you connect all the way down, that will be your Km. So that's an easy way to figure out your Vmax, your half Vmax, and your Km. So I'm going to go ahead and show you guys how to do the Line-weaver Burke Plot, which is a way to figure out what kind of enzyme it is, whether it's competitive, uncompetitive, or non-competitive. I'm going to talk about also what those are and how you could tell what it looks like, what's their Km, what's their Vmax, and how you know. So that's going to be the main. So hopefully write this down on a spare piece of paper. It'll also be below on a practice worksheet I will have for you guys. So, okay guys, these are the inhibitors that we'll be talking about, and this Km and Vmax and the relation it has to the binding and to the reaction. And inhibitors, what they do is they block where substrates can bind. So that changes what enzymes are able to do. It changes how fast the reaction is, and it changes a lot of things. And there's 3 different kinds of inhibitors that we'll be talking about today: competitive, non-competitive, and uncompetitive. So the 3 names are can be complicated, can get mixed up. So I'm going to show you guys how they affect the relation and the Line-weaver Burke plot and what happens. And these are all consistent. So competitive will always have a higher Km than the no inhibitor, and it'll have an equal Vmax to the no inhibitor. And no inhibitor means that there's nothing inhibiting the enzyme and the substrate from binding. That means there's nothing there to block it from happening. Non-competitive has an equal Km and a lower Vmax. Uncompetitive has a lower Km and a lower Vmax. And I'm going to show you guys how to get these things too. So for the Line-weaver Burke plot, so how do we find Km and how do we find Vmax? So let's put the Vmax and Km equals. How do we find these? So to find these, there are a couple different things we could do. So on the x-intercept, x-intercept equals -1 over over km. And then so in the y-intercept equals 1 over v max. So you guys can say, well, hey Adam, that seems pretty easy. It seems kind of straightforward. So what is, for the no inhibitor, what is the km for the no inhibitor? So this is a -2. So we're going to plug in -2 in the x-intercept equals -1 over km. Simple algebra, it'll be km equals 1/2, or -1 over -2, which equals out, two negatives equal a positive, so it'll be a 1/2. So km will be 1/2 or 0.5 for the no inhibitor. And I hope you guys see what I did. So this is also consistent. So it's for the on the Line-weaver Burke plot on the x-intercept equals -1 over km. However, these numbers can change depending on what's being catalyzed and what reaction is taking place. But for our example, for what we're doing, I'm keeping it simple. I'm going 1, 2, -1, 2. But these numbers could be anything depending on what's being catalyzed. So there's that. So let's see a y-intercept. Let's find the v max. Y-intercept's at 2. So 2 equals 1 over v max. So similar to what happened here, similar algebra, it equal also 0.5. So that is how we find the no inhibitor. So let me show you guys now what does a competitive inhibitor look like on a Line-weaver Burke plot. And this is also consistent throughout. So consistently, a competitive inhibitor will have a higher Km and an equal Vmax compared to the no inhibitor. So I'll show that I'll show that the line in red. So I'm gonna go here. So we have a smaller, greater Km. I'll show you why this makes sense right now. So here's what a competitive inhibitor will look like when compared to a no inhibitor. So Adam, I thought you just said that the Km was greater. Well, hold on, let's calculate. Let's see what we get. So to find Km, we're going the x-intercept, which is -1. So -1 equals -1 over Km. Okay, we're looking for Km here. So what do? We swing these around, algebra, and it'd be Km equals 1 over 1. So that means Km would equal 1. So Km has to be greater than the no inhibitor. So Km equals 1, Km equals 0.5. So which is greater? Competitive enzymes, our competitive inhibitors will always have a greater Km than what it would look like without an inhibitor. So let's do the same. So the y-intercept. So y-intercept is 2 and equals 1 over V max. We're trying to find the V max here. We switch these two, that would equal 1/2. 1/2 equals 0.5. And what do we know about competitive inhibitors? Is that they have the same V max. It equals. So V max, as calculated and how it looks, would also be 0.5. It's fairly simple. The line will always be consistent as well. So, and the numbers may change, but this line will be similar. So how do I look at that and just know it's a competitive inhibitor? Well, if you're not too sure about Km and Vmax values, a way I can recognize this, and a good way that helps me remember it, is if you look at this, it looks like there's two C's. So it looks like two C's are going back to back. So that's a way I can remember this. You see one, like two C's like that. And that's something we can see. See, here's one C. That's an easy way to remember. That's what helped me, reminds me that this is a competitive inhibitor. So let's check out a non-competitive inhibitor. And these are all in relation to the no inhibitor. So the no inhibitor is important to know. And it'll be given to you come test day. So let me erase these two. So let's look at a non-competitive inhibitor. We'll put that one in green. So a non-competitive inhibitor will look like this. So this is a non-competitive inhibitor. That's the way it'll look like on the Line-weaver Burke plot. So let's do the calculations and see if this is correct. This is as stated, Km is equal to the no inhibitor, Vmax is lower. So how do we calculate this, Adam? So we have x-intercept equals -1 over Km. So x-intercept is -2. So -2 equals -1 over Km. Swap these around, that'd be Km equals -1 over -2 plus plus, it's 0.5, so our Km would be 0.5. And does that equal? That equals, so we're in the clear, we did it, our line looks good, our graphs look good. So let's see Vmax. So our y-intercept should be 3 in this case, there's a 3. It's because it crosses the y-intercept at the 3, equals 1 over Vmax. Swap these around, Vmax equals 1 over 3. So our Vmax over here would be 1 over 3. So let's see if that makes sense. So 1 over 3, is that less than 0.5? Yes. So 1 over 3, it's approximately 0.33. So check, check. So that looks good. So a way that we can remember that what non-competitive looks like, so if they didn't give you any information, if they didn't even give you the numbers, and how can I recognize that this plot, a non-competitive enzyme, or non-competitive inhibitor, sorry. So the way I look at it is it looks like an N. So if you flip this around, it would look like an N. So that's the way I'm able to tell that so when it's flipped around, it looks like one small lettered N. So the non-competitive one is the hardest probably one to recognize just because of the shape it is, but this is the way I can remember it. There's one N. So that's that one. Now we're going to check out the uncompetitive inhibitor. Let me draw my graph again a little bit, this thing's getting messy. So 3, 2 there. Alright. So, I'll probably erase some of this. So, a uncompetitive inhibitor, it lowers the Km value and lowers the Vmax value in comparison to the no inhibitor. This is the no inhibitor, as we remember. Okay, this one's going to be in, let's do this one in blue. Haven't been showing blue too much love, so this one will be in blue. So a uncompetitive inhibitor will look like this, and this one for me is the most easy one to recognize. So once again, saying, oh Adam, well it says lower Km, why is this on the Km side, why is it less, or why is it greater than, or why does it look like it's greater than? Okay, well, we're able to check this out and see this and put it into comparison. So on the x-intercept, we're going to plug that in. So on the x-intercept, which is -3, equals -1 over Km. Swap these around using algebra. It would be -1 over -3 plus plus, and that would equal to about approximately 0.33. So Km would be in fact lower than the Km on the no inhibitor. So we could also see on the Vmax, it'll be the same math. You could go ahead and pause it and see if you guys could figure it out yourselves. I mean, we have our graph here and we can see what it is. So go ahead and pause your video now and see if you can figure out what the Vmax is for the uncompetitive inhibitor. Okay guys, welcome back. So the y-intercept is 3, and that equals 1 over Vmax. So how do we solve this? These swap places, and Vmax is equal to 1 over 3, which is also 0.33, which is also lower than 0.5. So that is a way, given the data, we can calculate all that we need to know. So in the uncompetitive inhibitor, we can easily recognize this without any data points, and a good way I'm able to do this, or I recognize it, and the way I have learned, which is I think uncompetitive is the easiest one to find, and it looks like a giant U for uncompetitive, just like N for non-competitive and C for competitive. So uncompetitive creates a big U. It's blocked, but it's a U. So that is the way we can recognize things using the Line-weaver Burke plot. And so oftentimes we may, on tests, they may give you guys just sometimes data points, sometimes they'll give you just the graph to recognize. So if they gave you something like this, now see, if they gave you something that looked like this one being the no inhibitor, they may ask you, what is this? What is the line in relation to the no inhibitor? And just being able to recognize the double C's, you'll be able to know that that is a competitive inhibitor compared to that of the no inhibitor. So fairly simple. You guys may need a review. These are very important to remember, so I would definitely go back and remember that competitive inhibitors, because this is constant throughout, that competitive inhibitors Km is greater than, the Vmax is equal to the no inhibitor. The non-competitive has a Km that is equal to a Vmax that is less than. The uncompetitive has both less than, so Km will be less than and the Vmax will be less than. So these are inhibitors, and this is what concludes today's video. The Line-weaver Burke plot is commonly used and commonly tested on, and I highly recommend to go over each of these and definitely know what Km what Km is and what Vmax is. So Vmax is how quickly a substrate can turn to a product, and Km, what is a better substrate as far as affinity? We'll hold on to a substrate better. Go ahead and like and subscribe, and please share the video to friends, family, anything. Thank you guys for watching.
Yay!
Yeah, that's that.